But I just wanted to know about your areas actually. What are your just give a quick introduction actually, so that like based on that I can pitch up what is your background. Yeah. Be taken. Okay, great, great. Okay. So you come from Bihar actually. Nagpur. Okay, okay. Paloti, Nagpur. Okay. Yeah. What about you? Yeah. Same institute and same background actually. So it's IoT industrial in second year. You're in second year part. Second year completed. Okay, good, good. Yeah. So what about you? Okay, okay. Oh,
Yes,
you're
I am.
11th grade actually.
Yeah.
Oh wow.
Yeah.
Okay, okay.
Yeah.
So yeah, so you have so you have any background on working?
I was an intern at Siemens
Okay,
Industrial Automation.
okay, okay.
We worked on PLCs and ACS.
PLCs. Okay, okay. Good, 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 good.
I am in first year,
Right.
WCM Nagpur.
For what
WCM,
WSM? Okay.
Venganga College.
What is your background actually?
BTech first year,
BTech first year. What is your area?
CSC.
CSC, computer science. Okay, okay, okay. I think rest of all I know actually they're all from my group. Okay, so I think what about you?
Sir, I am technical staff here.
Technical. Oh, okay, okay, good, good.
I have also joined PhD
PhD. Okay, okay, okay.
part-time.
Part-time. Oh, okay, okay. Good, good, good. Okay, so I think I'll make it. I know. I think it's a long day for you guys. I just don't want to spend too much bombarding with you a lot of things. I'll make it more interesting today's lecture. Like, I think tomorrow may be a bit dry. You may pay some bullets actually. So be ready with it. Okay, so I'll go with more of application part. I'll try to go with an application part. So I think my topic will be on something called soft sensors actually. Okay, so soft sensors for quality prediction, control and optimization of complex process, but I'll focus more on quality prediction kind of actually. Okay, so why we need these soft sensors? Okay, so why it is called soft sensor? We had hardware sensor. We know hardware sensors, right? So why we are interested in software sensors? It's called software sensors. Okay, let's get into the deep part and let's look into it. What are the methods? I think whatever last week that you have gone through it, what the entire week that you have gone through it, you can see how you can implement in developing this one. Okay, it's an integral. You are going to use those tools here actually. So where you can use, in which part you can use. Okay, so just to begin with an introduction of my area actually. So we work in systems engineering and data analytics. Okay, it's a mixture of. So we look at starting from data pre-processing. So given a process data, so how you pre-process the data, how you remove the missing data, outliers, how do you address the drift changes in the process conditions, okay. Then we look into something called developing of predictive models or something called virtual sensors or soft sensors, okay. And then if you're coming up with these models, where are you going to use? So you can use it for predictive maintenance, means can you able to predict early detection of fault, kind of, okay. So then, okay, that these are all predictive things. So can we use these predictive models for controller design and closed loop control and optimization part? So that's what we look into. So we look into multiple areas of something called systems engineering and data analytics, okay. So just to begin with, I'll just give an overall hierarchy of any industry. So if you look at any process industry, so this is the overall hierarchy that you face. I think you guys can see this actually. Those are sitting here, yeah. Okay, so this is what the overall hierarchy of, let's take any process industry, like kind of a refinery, okay. Start with a refinery, if you have a refinery, or if you have any semiconductor process or pharmaceutical process where you're trying to manufacture certain penicillin production or certain tablet manufacturing or something, or like any process industry which has several steps. So this is what the regular planning process steps which we have. So we have a unit, a process or a reactor, or let's suppose a nuclear reactor. Let's suppose you're trying to manufacture something through nuclear reactor. So you have a process or a plant. So where in order to optimize or safety, means to control or to maintain that process, you need measurements, right? You need to take some information from it. You need to keep taking some information. So that's the layer that you have immediately after from the process attached to it is something called measurement and actuation. So which takes the measurements from the process and tries to understand the behavior. Like let's suppose you go to a hospital, okay, with a certain amount of fever or whatever is the condition that you have. The first thing is that you will put some thermometer inside, right? So that you will get what is the condition of your body actually, kind of whether what's the temperature, what is the status of your temperature. So like that you have some sensors here actually, measurement and actuation. What is the temperature of the reactor, pressure of the reactor, what is the different conditions actually. So you have some sensors and actuation which are directly mounted on the any particular reactor. Okay, and from there you have the first layer is the safety logic. Depending upon, let's suppose if in a nuclear reactor the temperature is going shooting up. Okay, the first thing that comes out is the safety logic. Means there is a valve which is opened, which tries to open it immediately without any delay of second actually. Okay, so that you can regulate the pressure in the reactor, and then you have something called regulatory controller, multivariable, real-time optimizer, planning and scheduling. These are top layers actually. Okay, so but these all layers depend upon what the information that is going from here, right? There is the first information. So that's the thermometer that has been kept in your when you have fever. The information that you get from the thermometer is the most critical thing, right? The temperature of it. Based on that, the doctor prescribes what conditions have to be given to it, actually, which tablet has to be given or what other precautions have to be given. So based on that particular. So the measurement information is critical going from here to the upper layer. So what information is going from process? Okay, that is very critical. So is this information available continuously is the question. So I think people are from different backgrounds actually. So let's suppose those who are from electrical or electronics background. So if you're driving a vehicle actually, okay. So you wanted to know the speed of the vehicle it which in. So you get constant measurements, right? You have sensors actually in your vehicle. Actually, you get to know what is the speed of the vehicle with continuously. Based on that, you take decisions. Either you slow down or you go faster actually, because you have sensors placed which are giving continuous measurements about the way you're going. Okay, these are continuous real-time measurements. But what about some process like let's suppose take a case of a medical condition again. If it is a fever, it's fine. But let's suppose you have a serious medical health issue. So when you go to a doctor, so what does he do? Will you get medicine immediately? To do some test. Okay. Are the tests are real time available? You don't get the test real time. They'll take some delay. There is some delay associated with it, right? Actually, he will write a test. You go to the doctor, do the blood test, and wait for certain amount of period of time. Then you get a sample, whatever the report is, 1 day or 2 days. Then you get it. Based on that decision, again he will make some changes actually. So in the case of automatic car, you have seen that the measurements are continuous and you are able to take the decision. But in the case of health condition, you can see that the measurements are not continuous, right? If you are continuous, if you are able to get continuous measurement, then you can immediately solve the issue actually kind of. But there are lag in the measurements. Okay, the samples are lag. They are taking at least 1 day or 6 hours or 8 hours actually. Like that in process industry, when you come into the process industry, so the measurements that you get from the process may not be in real time actually. Okay, let's suppose you're controlling a nuclear reactor or something. So you take one sample to know what is the status of what you're manufacturing. Okay, so the sample that you take maybe not be every second. It will be like 6 hours, 12 hours, 18 hours, 24 hours. Like that one sample you take, you measure and check whether the sample that you selected is desired quality or not, and based on that you make corresponding actions. Like how in the case of medical health, you get a sample and based on your medical history or whatever the reports that you got, you take a corrective action. Okay, like that in the process industry also, the samples are coming at 6 hours, 8 hours, 12 hours. What is the problem with this? Let's suppose you are manufacturing some nuclear bomb or you are trying to maintain it, okay, and you are getting only the sample at every 6 hours. And if there is a sudden blockage or malfunctioning of the coolant which is surrounded outside the reactor. Coolant means the coolant water which is going to surround outside the reactor. If there is a blockage of that flow of the water, what happens? The temperature will shoot up because you don't have a real-time measurement there actually. The measurement that you take is only 6 hours. Only 6 hours or 8 hours, 12 hours, 14 hours you are taking. But you don't have any real-time measurement coming from the reactor. The real-time measurement is only coming at 6 hours after. But I need a real-time information. At every 1 second, if I get to know for the reactor what is the status of the conditions, then immediately I can try to control my process or I can be able to regulate my process. Okay. So if the process is slow, like a kind of a health deterioration, then generally the health deterioration may not be severe, health deterioration may be slow. So even 6 hours, it's okay. But if, let's suppose in the case of nuclear reactor, the temperature shoots up very rapidly. The temperature shoots up rapidly and you are waiting only for 6 hours to get to know what is happening. Is it safe or not? It's unsafe, right? Again, there's a chance of getting a blast of complete reactor itself actually. So the hardware sensor which I'm doing it is giving 6 hour sample. So what should I do here? So, but if I reduce the sampling time, the cost of sampling is higher for me. Let's suppose one sample goes to lab analysis and you need to use some hardware equipment which is very expensive. Okay, so I can't do this reduction of the sampling time because I need to avoid this manpower and the cost. But this all data is available. The reactor is mounted with lots of sensors like IoT, like those studying IoT. There are a lot of sensors are available. This data is all stored in the database. Those are also stored in the database. Can I use the data to come up with some predictive model? If I can predict the temperature of the reactor in real time, rather than waiting for 6 hours, if I can predict every second measurements actually, will it be beneficial? I can take a decision, right? I can take a decision immediately rather than waiting only 6 hours when the sample comes, okay, this is what the condition, and go back and change some flow valve or something like that change. Rather than doing it, I can immediately take a decision. Okay, so these are called soft sensors or virtual sensors. Means we are not depending on the hardware device mounted on the reactor. We are now coming up with a model which I can plug it in my computer, and what all the conditions that are being given into the process, I give it to this part. Okay, so it is like this. Is it clear? You are able to get it? Okay, so we want to avoid using the hardware sensors as much as possible. What is the difficulty with the hardware sensors? What if the critical sensor is there? That goes bad. Your temperature, you are able to measure the temperature of your body, but the temperature sensor has malfunctioning. Rather than 98 degrees, it is reporting 104 degrees. Then the decision is different, right? You will take a wrong decision. Okay, you will take more paracetamol tablets to address it, but actually the temperature is 98 only. But you are taking 104, it is predicting that 104. The sensor is problem. Hardware sensor is a problem. Okay. So if I use more hardware sensors, there are chance of erroneous results. So I want to reduce hardware sensors as much as possible. Critical sensors, not all sensors, critical sensors. Like a critical variable, let's suppose a variable is there, which there are some sensors you can get fast measurement, like a flow rate sensor, like a water flow rate, flow sensors are there, which you can get every second measurement actually. But there are some sensors like concentration of quality concentration, which you cannot, like as you was asking, can we reduce sampling time? You cannot reduce sampling time. If I reduce sampling time, I need to invest more money in analysis part. Okay, I need to invest more money in analysis part and to buy more equipments. One equipment may cost 5 crores. I don't want to buy multiple investment. I want to reduce as much as economy. Okay, the money which I'm going to spend on it, I want to reduce it. So, so I wanted to come up with something called the soft sensors. Whatever you see that now you are learned machine learning, the supervised learning part. So can we use a supervised learning efficiently in the industrial scenario? Okay, so let's suppose you have a process of any reactor, of any process which is happening, which is affected with certain inputs. Inputs are like the one which drives your process, and you are getting some measurements. Why? Okay, but these are coming not at continuous. These are coming at every 6 hours, 6 hours, 6 hours. So in order to know this process condition, these measurements are coming only at 6 hours intermittently. Okay. It is like your health condition, body condition, you are getting reports only at 1 day, every one day, or 1 week. Let's suppose you are in a very remote village, you don't have actual resources of lab facilities and all, the sample comes 1 week. Then what happens in between? I'll be done, right? My health deteriorates till 1 week. Rather than waiting, like my body is like my reactor, right? I'm trying to protect a reactor here, conditions. The same way, if I have a health condition, so I need to get frequent updates from the reports actually. So if I get 6 hours, 6 hours, 6 hours, then I'm going to, there's a problem. In between, I don't know what is happening actually, right? So in order to avoid that, I'm interested to come up with something called virtual sensors or called software sensors. Or soft sensors means software sensors. I'm going to use software actually. I just use whatever the data that is being available on the reactor and stored in the DCS, which we call all the data is being accumulated. Can I use the data, real-time data, which has been present over the last 10 years or last 6 months? What is the data? And come up with a predictive model where now in the predictive model, this is my computer. Okay, this is my computer, and this inputs which are affecting the process. Okay, these inputs can be, if it's a reactor, it can be water flow rate, it can be inlet temperature or whatever it is. For chemical engineering process, students can understand easily this part. You can relate to your own system. Like let's suppose if you are driving a vehicle actually and you wanted to increase the speed of the vehicle, the output is the speed that you are interested and these are input is the accelerator, right? You're trying to increase the accelerator kind of. That's the measurement is the speed that you're measuring. So these are the inputs which are driving the process. So the same inputs now I'm going to send it to my computer, where in the computer a model is sitting here. What is the model that is sitting? Y equals to f of u1, u2. What is y is output and u1, u2 is input. It's a supervised or unsupervised learning? It's a supervised learning. You have a clear distinction of output and input variables and the labels are clearly defined. So can you come up with a model y equals to f of u1, u2, so which you can plug in your computer, okay, and now send the inputs which are sending it to the process. These inputs are similar inputs send it to the model also, okay. Then I can get what? I can get the predictions of output, the speed of the vehicle or the health condition or the reactor temperature condition at every second, millisecond, whatever I want. If I increase my computational speed, I can get every second predictions. I'm going to get a predictions. Is it clear? Okay, so when that guy comes, take the sample and go and do the analysis. It takes 4 hours and comes back and says that this is a sulfur dioxide for the previous day. But in between, pata nahi. If something happens in the process, SO2 can be higher or a lower. Lower is fine. It will be dangerous, but I need to monitor it, right? I don't have any sensors to monitor. Hardware sensors are not there. You have a hardware sensor, but which are costly, which I need to do it every time actually kind of. So I need to do some analysis, lab analysis, and send it to the analysis part. We call hardware devices are called analyzers, which are very expensive. Let's suppose you have 4 reactors, and 4 reactors are emitting sulfur dioxide. Okay. By suppose I got some funding from the manager and I put one reactor to one hardware device to particular, so that I can measure sulfur dioxide. But what about other 3 which are emitting? One hardware sensor costs 5 crores. Should I use the same thing? Suppose you guys go back now, BTech students who are there, go back to managerial level. You are all interested in the managerial level, right? MBA or okay. And you have been given this position of reducing the cost. What do? I want to do a cost reduction, not cost expansion. You have been given some amount, you reduce the cost and maintain the conditions. You need to maintain the sulfur dioxide conditions, but with this budget. What is our choice?
Sir, but in process industry, it is always assumed that if we are following similar process everywhere, the emission will be similar.
But what happens? Some input conditions are changing. Let's suppose one reactor, one particular plant is working at a desired conditions. In other plant, you change your input or the operator is new, it doesn't have a conditions of what operating conditions are to be changed, he changed it to some other level, then there is a chance that the output is getting affected. If it is good, if it is all stable, it's fine. But we are discussing about abnormal conditions. Yes. Yes. We'll come. We'll come there. Okay, that's a good question. Let's not get into predictions wrong. Okay, if they are wrong, we'll have some tablet again to correct those predictions. Yes, that's a very good. So you are saying that, sir, you are now saying that you will depend entirely on the prediction. This can be a wrong actually. Yes, that can be wrong. That's what I was questioning about adaptability, model adaptability. You developed a model today. You're going to put it tomorrow online. After 1 week, the model predictions will go bad. How do you adapt the model in real time? Okay, so whatever your question is valid, this model can be a wrong. Okay, but before incorporating, we will do a lot of analysis. We won't directly go and put it. It takes years to go in an industry, in a big industry. If it's a small reactor working in a lab or something, you can plug in and check it. But if in an industry which is connected with multiple reactors and harmful chemical emitted, they won't give permission to immediately put your machine learning model into the system, where it can be a devastating also. Right? If it predicts wrong predictions, let's suppose the ppm levels are, actual ppm levels are 8 ppm or very high ppm, my model is predicting around 0.001 ppm. Right? The operator doesn't take any decision who's sitting there actually kind of. He says that everything is working very fine because the model is predicting. So I need to trust the model. So there are a lot of rigorous verification, validation has to be done before putting it into the actual process. So we'll show some case studies where we have implemented in real time. In real process industry, we have implemented and we have seen that how the performance of the models are there actually, and which are working, which have been replaced, the analyzers have been replaced with this part. Okay, so we're going to show that. Fine. So this is a case of a supervised learning. We are going to go in the next today and tomorrow. We are going to discuss the supervised learning part. One application of supervised learning, but different abnormal conditions. We'll take different abnormal conditions. In those conditions, how your model has to be tweaked. Okay. So because the data doesn't come with we'll see the cases. Fine. This clear? The soft sensor is a model, a supervised model, which you're going to plug it in your computer, take the data, historical data, train the model, put it in your computer, and send the same inputs to the process as the same inputs to your computer, and predict and get a real-time predictions. And you monitor these real-time predictions. Okay. Yeah. So good. So this good. So I was saying that now comes the problem. Okay. So if you have a one reactor, it's fine. Okay. If you have one reactor, developing a model is simple. Fine. So I think chemical engineers can get into this part easily. So if you have one simple reactor, I want to predict an output. So what is the problem of first principles model? I had an introduction of first principles model. We call first principles model. Other domains. Use your physics, means physics. You learn, you're an engineer, let's suppose electronics engineer, electrical engineering are there. You use your physics to model certain system, right? Actually, physics-based models, mass balance, energy balance equations, okay? So let's suppose you have one particular reactor, is there, simple reactor is there, and you have an input and you have an output which is coming. So this is some process undergoing. So if it is one reactor, I can use my simple, my entire BTech chemical engineering, whatever I've done, some fundamentals part, mass balance, physics. I'm going to look at the physics part, not at the data. I'm going to look at the physics part, understand the behavior of it, and come up with certain model. I can come up with certain model how the variable in the reactor is changing with respect to particular with respect to time. So I can do get some differential equations by using mass balance. But industry process are of this nature. Okay, so here I'm interested in order to this is one example of a practical benchmark example of a typical refinery. Okay, so you have a product which is coming at the bottom of this particular process. So the aim is I wanted to predict this product in real time. Initially we were looking at one system. Now it's a system to system. You have multiple connected processes actually connected actually. I am interested in order to predict this product quality in real time. Fine. Can mass balance, energy balance work here? Physics? It's complex, very complex. You can do it, but it takes at least 1 year. And I need to pick some chemical engineering and put it there. Okay, let's suppose now we have computer science students are there here actually. Okay, the same problem I give to computer science students. Okay, so I'll tell you guys that all the data is available. This variable data, output data is available, and all the variables which are affecting the output also is available. So how do you start now? I want to predict this. Let's suppose this is a black box. Which one is trustable? Which one is trustable? Which one is trust? Which one you mostly depend? One is data driven, you are just building the data. The other is physics you are using. You are actually using physics, what is happening? Which one is more? Data model, real picture of what is happening actually. Okay, yeah. This is a physics one. Okay, if we can able to wait for 1 year and I can recruit, so I'll go with the physics. Actually, you should do that actually. If you have a physics knowledge and if the process you are able to, if it's this challenging, but if you are able to come up with a model, but 1 year lag is there. Okay, if at least the validation and all takes 1 year part. Okay, so one has to, and you need to find a right candidate to model this. Okay, you need a chemical engineer to model it. Let's suppose if it is a mechanical system, you need a mechanical engineer to model that system because I can't understand a mechanical system. I can understand a chemical system. So you need a domain expert. Okay, but if you can able to get a domain expert and model it, that's the best model that you can get because you are covering the physics part of it. Okay, but here we are looking only at the data. Data, we are just taking, let's suppose last 10 years of data is available in your historical data. You are only taking that data set. What if a condition has come that was not there in the 10 years data set? Can your model work? It will work? It won't work, right? Because it has not seen the data. But what about physics-based model? It will work because you consider all the conditions. Okay, there are drawbacks like both the pros and cons are there. If you are going with the data-driven model, it's faster. You can easily develop it actually. Maybe within an overnight, if I give you data by morning, you can come up with some model part of it. But the same thing is that though it's easier to develop, validation will be quite challenging or real-time implementation will be very quite challenging because the conditions keep on changing, the process conditions keep on changing, right? Like let's suppose I'll take the example when I teach this machine learning to my students. Actually, I'll take the example of let's suppose I'll take one example. Let's suppose this is a student actually. So I daily observe this student actually kind of, and I can predict the behavior of the student. Okay, how this behavior over a period of time. Okay, but later on he has taken a break and there is one more new student has come actually kind of both friends. But will that behavior of the both of them will be same? I have not seen the other guy behavior. I have seen only this guy behavior. I can't predict that behavior, right? The drawback of this one is that you can't extrapolate. This model cannot extrapolate into new system. If the new disturbances are coming or you cannot extrapolate. But physics-based model can do that. Okay. But the challenging with the physics-based model is time consuming. Okay. The time consuming and you need a domain expert of that particular area. Okay. Okay. So yeah. Physics-based models. Yes. That's good actually. So we will get into the classification of models. There are different kinds of models are available. One is purely physics, one is purely data driven. There is something called combination of it. A physics and a data driven part. It's a hybrid model. We call it a hybrid model. So we are actually in this lecture is focused on more on hybrid model. Rather than just going with a physics based, can we come up with some knowledge of the process? Okay. So let's suppose y is getting affected with certain variables. Can we have some relation between the variables actually around and incorporate that in your model? Okay, so that you are not losing this touch, you are trying to merge both data driven and the physics. You understand? You are taking some part of knowledge, physics knowledge, what is happening in the process and putting it in your model actually. So that you are not only depending on data, you are also incorporating some amount of physics knowledge. Okay, these are called hybrid machine learning models, okay? So which are quite popular, which are actually trustable when compared to going with these both directions, okay? So, fine. Yeah, so this is a challenging thing, means developing the models for this kind of thing will be challenging.
So,
yeah.
So what if data is not data is not clean? So it would be very difficult to clean the data, and it will take
Yes,
time.
we are going to get into that part. Just hold on. Yeah, that's a very nice question. Okay, so data, you won't get nice data. Okay, nice data you won't get. So we'll come to that. Okay, so that is what the talk is focused. Yeah, the data cleaning is the first key thing of your machine learning model is the data preprocessing. Then once you data preprocessed, tools are there. You just plug in the data, you'll get the model out. But cleaning the data and making your data rich. Okay, so that's the thing. Okay, that's a good thing. So you know now I had an idea of importance of soft sensors, right? You understand the importance of. So in a controller, let's suppose you're trying to control a feedback. So I think those who are non-domain. So who doesn't have any idea of control? Okay, I'll tell you. I think you have an idea, but you never saw it actually. Now I think the temperatures are going down, right? It's becoming cooler, right? So when you go for a shower, what is the first thing that you do in the morning? When you go for a shower to take water, what is the first thing that you do? Temperature check. Okay. So you open the valve, take the temperature reading, right? You sense it. You are sensing it, and based on that, what you do? Adjust the temperature. You keep changing the valve position. How much amount of, let's suppose there's a hot water, there's a cold water. and you keep open both the things and try to adjust how much amount of valve has to be opened, closed by sensing it. You are sensing it and closing it, sensing it and manipulating it. It's a feedback loop actually, kind of. Okay, so your brain is your controller, okay, and you are trying to sense it through hand and you are manipulating it. The valve is manipulated actually. You are manipulating. It's a closed loop. It's a closed loop controller, like case of like agriculture. Let's suppose you have agriculture systems. So how much amount of water has to be supplied to an agricultural field? How do you know? So you measure the moisture, and based on the moisture sensor over a particular region, whether it's a desired moisture or lesser than the moisture, based on that I take corresponding action. I'll increase the irrigation rate. It's a closed loop control. Okay. So for all this, we need sensors, right, to measure it. Like for the case of morning water, you're saying you're sensing it. Then only I can take an action. In the case of agriculture part, you need to know the soil moisture content, humidity, or whatever moisture content you need to know. Then only you can take an action, right? So the similar way, in the case of, let's suppose you have a reactor, any particular process reactor is there, and I wanted to, this output is my soil, let's suppose many desired value. If I want to know this desired value, whether it is at a desired condition, this is a variable which I am interested, whether it's a desired condition or not, like soil moisture. So you wanted to regulate the ground soil moisture at a desired value. Okay, that is your goal. But in order to know that, you need to measure first. Without measuring, how do you know it actually? Okay, so these measurements may come intermittently, like delayed measurements, like we were discussing, and you can get a continuous measurements. Okay, so if the measurements are delayed, so then you need something called soft sensors or virtual sensors, which can predict these delayed measurements coming in real time. Okay, and these real time measurements can go to your controller and take it actually. Like if you are this is like my health system, my body actually, and I'm having a severe health conditions, and I'm getting the reports at every 6 hours or 1 day or 2 days, and I use these report conditions, and I have some sensors which can predict my real time information of it. Then I can actually plug in, let's suppose a glucose sensor is there. You generally get a glucose controllers, okay, like how much amount of, it will test your glucose level and how much amount of insulin has to be injected. Okay, kind of. Okay, it will test the real-time glucose and try to manipulate the insulin content. Okay, so like that, soft sensors plays a role in controlling the process. Initially, we are doing only predictions. Actually, you can use it in a closed-loop control part. Okay, you can get a real-time measurements of this variable and try to make the corresponding actions and do it. Is this clear? Okay, it is more into control. This is a closed-loop control. We are saying you have a process. These measurements are coming. But these measurements are not continuous, they are discontinuous, so you use these soft sensors, means machine learning models actually. So I'm just highlighting the importance of, before getting into the actual story, highlighting the importance of where you can see machine learning part in the actual process industry. Okay, kind of, okay. So the supervised learning, but specifically the supervised learning part. So use supervised learning to predict the real-time information of variable and then send this information to your controller takes an action accordingly. Right? Yeah? Okay. So, I'm just planning to, here is outline of the presentation or the next day talk actually, whatever I am planning to do it is. I think importance of sensor we covered and classification of sensor. We'll start with a simple regression model, okay. We'll see how, for this particular, for a process, how do you develop a simple regression model. I think already it has been discussed, I think regression has been touched upon. So, but we'll see what is data preprocessing, how do you do it actually kind of for a regression, and what are the problems associated with the regression, like how he was mentioning about data doesn't come neat actually. So what if your data is bad? Can a regression model can be modified? A simple regression model can be sustained if data has noisy data. Okay, how do you modify these regression models? So regression models are not adaptive to it. You need to make your regression models into probabilistic sense. Okay, so whatever we have looked at, I'm sure I think the last classes what you have looked at is more into deterministic regression. So you did not assign any randomness to your estimates, kind of, okay. It's more on deterministic part. We'll look into more of probabilistic sense actually, kind of. So the same regression problem we can take and try to formulate as a likelihood problem actually, okay. So it's called maximum likelihood estimation, and then we will see something called probabilistic graphical models. Means, okay. So what if you know how output is affected? Let's suppose I'll just give an motivation and leave it to you. So you can see here, okay, this is the output, right? This is the output I'm interested. Six is this is like a simple, a water is entering into it, a hot water is entering into it, and it is getting splitter. You use a splitter, it's a process industry. In any process industry, you will see this. You have a splitter, the water splits into two regions, 2 and 3, and then there is a valve, and the water comes back again and mixes, and you will get an output. Okay, I'm interested in order to predict this one. If I'm interested in predicting this one, what is the generic regression that you do? You take all the inputs and fit a model. Okay, that is one way. Okay, input and output data. You have 5 inputs and 1 output, you fit a model. But now I know a flow structure here, right? Can I come up with a network structure? I'm using some physics, what is happening here, into my model part. Rather than just a regression fit, can I use some model information saying that 4 is affecting 6 and 5 is affecting 6 and 2 is affecting 4, 1 is affecting 3. Some kind of behavior, the flow information into my model actually and train my model. Okay. Rather than just using a regression fit between input output data, I'm using some kind of structure kind of. Okay. So this is called a one kind of hybrid model or a graphical models. We are going to discuss this this part, like how you are going to use this structure into something called like this kind of structure, coming up with different structures. Can you able to come up with a, rather than just fitting a simple regression model, can you able to come up with, use some knowledge from the process flow diagram or process information, flow information, and fit a regression model. Okay, so which can address the issues of noisy data, outliers actually, and the cleaning of the data. Those things can be addressed. Okay, so yeah. Yeah, so that's what we call probabilistic graphical models. We'll just touch upon the probabilistic graphical models, which are quite intuitive. Means when you want to club your some physics information into your process, this is one way of doing it. Understanding the process flow diagram and trying to build a regression model or fitting a regression model accordingly. Okay, so in the probabilistic sense, we look at in terms of probabilistic sense, how do you do it? So these are some important skills, like those who are doing research part. Actually, you need to know this. Rather than getting into deterministic part, you also need to have a touch upon probabilistic sense, which has good advantages of addressing critical issues like noisy data, outliers in the data. Okay, so those things will help you. So it will be more, some theoretical will be there. We may derive some things actually kind of, so which can be helpful in the later part. Right? Yeah. So I think you guys want to, should I take some more time? You can take it? Yeah? Okay, I think I'll just take 10 minutes. I think 4:45 we can stop. I think maybe tomorrow morning we can go. So I think, yeah, this is the thing, just to motivate why we need a soft sensors or a predictive models is hardware analyzers, which I'm going to use in a real process industry, are quite expensive. They may cost crores. I want to reduce that cost. And can I use the data available in the historical databases? Okay, can I use the data? That's the main motive of predictive models or soft sensors. Can I use the data available in the historical data and come up with the predictive models? So, because why we need, let's suppose there are 2 industries that I'm taking here example. One is a pulp and paper industry. In the pulp and paper industry, the texture of your paper, whether the texture of your paper, quality of the paper depends on the kappa number. There's something called kappa number. Okay, that quality sample they takes every 6 hours. If that sample is bad, entire production of whatever you got is gone, lost. Again, you have to go back and change the parameters. Okay, some parameters have to change. This quality of this kappa number is checked only at every 6 hours or 8 hours, 12 hours. In between, if there is anything malfunctioning or some changes are happening, the quality may degrade. So, whatever the production that you have done in that range is lost. You lost your production. It's lost. Economy is lost. Again, you have to go back, change the parameters, and come back. Okay. The other thing is oil and gas industry. Like I was telling about release of harmful variable like sulfur dioxide or hydrogen sulfur actually kind of into the atmosphere kind of. So you need to monitor real time these sensors actually. So because you monitor only at every 12 hours there. Okay. You need a real time monitoring so that it affects, creates a safety atmosphere as well as I can actually manipulate or improve my economy of the process. I need to monitor these variables. So these are the major 2 advantages. I think you can relate it to any other industry, process industry, where you use or let's suppose we are also having some applications to ocean engineering where we predict ocean critical variables by using these predictive models. Okay, it's just a prediction here, but here it's a closed loop automation control part. Yeah. So yeah, the substances are classified into 3 layers. One is a data driven, one is model based. Model based is what we call physics. You use physics knowledge of your own engineering domain. Okay, engineering domain. Okay, you're trying to use the engineering domain, and those are called model based substances or first principles. And the last one is called gray box. So the first one is data is called black box. You don't see anything, right? It's input and output. You just have no understanding of the process. You are just looking at the data and trying to find a correlation between the data. These are called black box models. Whereas the second one is first principles or physics-based models, or model-based substances. And the last one is gray box, means you are mixing combination of physics and data. So I can have some understanding and some not understanding of the process. Okay, that's called gray box models. Okay, fine. Yeah. So yeah, the benefits are huge. Actually, I will show some examples. Like maybe at the end of the session tomorrow, we'll have some industrial case studies where we show that how much can impact an industry actually, kind of some predictive models. It's a simple regression models. If you can able to make it well, they can impact industry in billions actually. They can save billions actually. Because if you can able to come up with some predictive model of hydrogen sulfide or sulfur dioxide, which is accurate, they can replace the analyzer completely, which is of 5 crores or 6 crores, and one can use your model, predictive model in real time actually to predict these variables. Okay. So this figure gives the this part. So you have a process, you have a controller. Controller takes action based on the input that is receiving from the process, okay, which are called substances. Substances provide the state information, what information that variable is there. Okay, so based on that. So generally you have analyzers. Analyzers are the hardware equipments which can measure the critical quality composition variables, but they're very expensive. They're very expensive kind of. So in order to avoid this, one wants to shift it to data-based or data-driven substances actually. Okay, so one wants to shift it because they are very costly, expensive. I don't want to use this costly analyzers. Those, I think those who have any background on refinery, those who have gone into internship or something like that, you can easily see this. You can find these analyzers information there actually, kind of, okay, which are very costly. And these are hardware devices. What if this hardware device goes bad? Into maintenance. Let's suppose it is running, though it is giving every minute measurement, what if this goes bad? It's a hardware device. It has its own maintenance issues. If it is down, then I have to rely only on lab sample 12 hours, every 12 hours. I don't have in between anything to take any decision. No measurement or nothing is coming, the process. Only 12 hours, one sample is coming. I have to take, based on that, I have to take a decision. So let's suppose I'm manufacturing something, crude oil, or refining a crude oil, actually, which has to go to refineries, okay. Whatever I produce, if it is not off spec, it is off spec. Entire thing is lost. Product is lost, complete lost. I lost economy. So can I use data-driven models, which are data is saved, everything in the DCS? Can I use the data effectively and come up with some good predictive models which can predict in real time actually? Okay, that's a major advantage of it. Okay, I think we can stop over here. I think tomorrow we will discuss about. We'll start with a simple regression and go with probabilistic. So you can derive. We will try to derive in through hand, like how you can come up with a probabilistic model. Okay. And then editor based how you convert into probabilistic models, how you come up with the network structure models. We can try with simple examples and show that. Okay. It is not only just a data-driven model. That's what it can be a physics-based model, which can predict. It can be any sort of model. It can be a data-driven, physics-based, or it can be a combination of both data-driven and substance. So it's just it's a model which can predict a real-time measurement of it. Actually, yeah. Yes. That's a model. Yeah. No, we don't have any layer. Like you can have a data pre-processing layer. Okay, so generally that is being done before you are training the model actually. So we'll see how you do it. Okay. So, but let's suppose you have given a clean data, everything. So if you have a model, which model you want to fit? If your model is accurate, you validate it accurately, then I can plug in my computer. Okay, and I can send my real-time inputs conditions to the process, and I can actually see my process conditions. Yes, 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 yes. Yeah, yeah, we'll see that actually. I think next we have a step-by-step procedure of how to develop a predictive model or a soft sensor. So the first thing is a feature extraction. That is the most critical thing. Like in this case example, if we go back here, so this is one variable which I'm interested to predict, but there are almost 14 variables which are affecting this. That is 14 variables is quite less. Actually in industry, real industrial process, if you see a flow chart, you will have hundreds of variables which are affecting your output. So which variables you select as inputs? Variable. That is critical, right? Can I develop a 100 input variable with a output variable? Why? I can develop. Good advantages or not? Okay, that's good. Okay. What is the problem? My students are smiling. Dimensional complexity is there. Okay, that's okay. Let's suppose I will build a model. Forget about dimensional complexity. I'll do it offline and do it. What is the real issue that I get when I implement in online? I'll use high computer. I have 100 inputs are coming into my, let's suppose this is my model, y equals to f of u1 to u100. There are 100 inputs are entering into the process and I need to monitor this all 100. And let's say you build a model between 100 inputs, one output. Good. It is giving very good result. That's very good. Now I put it in online. What challenges you get? Transparency. More than that, there is something else. Huh? Okay. Think of manager. Manager, I'm explaining. And I am coming up with a 100 input model and one output model. As a manager, what you see if you want to implement this in real time? That's it. Why I need to worry about 100 variables? I just need two variables. Give me two input and one output variable. Why I need to put 100 sensors there actually? I can reduce the sensors, right? If I can able to get a result of two input, one output with 100 input, one output, which is the best model? Because the maintenance cost is very low. No need to have 100 sensors here, right? I need only two sensors which are significant. If I can select the features, these are called features. If I can select exact features which can have an impact on output, then that's the problem is solved actually. Regression is forget about it. Whatever the models I can use it. Features, if I can get a very low features model which can predict output, that is a problem is almost solved actually. Okay, but the manager appreciates you saying that okay, this is the best model when compared to 100 input model actually. Why I need to be worried about 100 sensors? Because I need to keep looking over the maintenance of 100 sensors. Rather than that, I only look at about this is much lesser efficiency, lesser input. And the other thing is, are 100 inputs are affecting output? PCA. Use PCA there actually. Are 100 inputs affecting output? May not. Only one or two variables are affecting. Remaining all variables are behaving in a similar way. Use PCA and try to extract the features which are independent. You may get only one or two features and build a model with it actually. Right? Feature reduction has to be done. You need to come up with a feature reduction. Right? Yeah. So you need to reduce that features. So we'll look into step by step like feature reduction, this part and all. So then we'll get into this part. Yeah. I think here we'll stop here today. Yeah. So then next class we'll go into this part. Okay. Yeah. Thanks. Any doubts? Anything is there to discuss? Yeah. You can feel free to. I think we have some time. Yeah.
सर जो भी दो इंडस्ट्रीज रहती है वो सिमिलर नहीं रहती, राइट?
Though in industry there are two plants which are different.
So I think that each industry will require different kind of model.
Yes.
So we can't implement one model.
Oh no, you can't. System is different. outputs are different for this process.
So we need to change the y function.
Why and this? No, entire model may be changed. Let's suppose here, discuss that. Let's suppose y equals to ax plus b. Simple model, linear model. One input is there. One input is there, one output is there. Let's suppose what are the unknowns here? A and B. A and B are unknowns. You have X data. Let's suppose this is a milk industry. You have a data of Y and you have a Y X data for a milk industry where you are predicting some variable carried, some important variable of milk. This is, or rather than the suppose weather prediction. You are doing a weather prediction. You have some inputs which are affecting your temperature, day temperature. You are predicting a weather prediction. Okay. And what are the things that you need to estimate here? A and B. If I know A and B, my model is ready. Okay. Now let's go to this is weather industry. Okay. Now let's go to chemical process, and I am also selecting the same model. Chemical process. So let's suppose this variable is some quality variable, okay, like concentration of variable. This is a temperature. This is temperature. This is concentration. Okay. So what are unknowns here? So can I replace this unknowns here? No, this is different process and this is different process actually. So the data that you are handling is different. The parameters are different. So again, you take this data, input data, output data, and re-estimate this A and B parameters. But this system, so you can't transfer the models. Nowadays
We can't transfer the data of one model.
completely, depending on the system to system. Let's suppose if in the weather conditions itself, if I'm predicting a temperature at different day conditions, so you can use the same model. But system to system, there are model changes. I think nowadays you guys are getting this pre-trained models, LLMs or PTM models, where models have been trained on one particular system and one can use it. But you need to be careful whether which you are using. If it is a trained for a weather condition, you can't use for a reactor. Right? The data set is different, and the model has been trained on a different system. You need to retrain the model. Conditions, process conditions are changing. Let's suppose weather conditions may be of a cyclic nature. Right? Agree? Summer, winter, summer, winter, summer, winter. My process doesn't operate in cyclic conditions. My process operates in steady state conditions. If I use this data to predict this one, you will get wrong inputs, kind of, right? I said, right? You understand? Yeah. So, yeah. So you need to be careful of using one data set to a completely yeah. It will not use models. Depending on the system, any data system. Yes, sir. You can go see there is a Kaggle data. Kaggle or you can easily understand like, what is happening, what variables are there, good quality. Kaggle have a lot of yeah, lot. So nowadays, like, you don't need a computer to run this programming and everything. So a lot of sensors we have like those, like you can see on the drone, the drone part, capture the data from surrounding images, yeah. We were working there. It's NIT National Film is there. you have a background or programming background.
I was trying to get it for training program.
There is